So thank you to the organizers for inviting me. I know it's been a long time. This conference has been in gestation since pandemic times. So I haven't traveled internationally since 2019. So I wedged a bunch of things in here. We'll see how far I get. So actually, before I start the main topic, let me just advertise something briefly, because I know there's a lot of quantum dynamics people here, people working on quantum circuits, and there's something we've been working on in a completely different context that I would love a better tool for. So again, just a short advertisement. So the question is, if I have a strongly interacting many-body quantum system, and we have in mind something particular, it's a strongly interacting fermion boson soup, it's technically a marginal Fermi liquid with Planckian dissipation and disorder, then the question is the hydrodynamic modes of that many-body quantum system. Are they classical or quantum? And in all my experience, what I've seen, discussed in the context of QCD or, other types of strongly interacting systems, yeah, quantum mechanics is important for the interactions of the constituents, but it seems like people usually assume that the long wavelength hydrodynamics are classical. And so I just want to point out that we have a bunch of papers in the context of strange metals and how can they pair, and I don't want to get into any of this physics. I don't want to get into any of the technology because it's ancient sigma model stuff that probably all of you would hate with good reason. But I just want to ask this question, so we have some evidence in these papers. This is work done by my student TC Wu in collaboration with my former student Yunsheng Liao, and the second part with Patrick Lee. Some evidence that hydrodynamic modes can still show quantum interference phenomena in the sense of things like Ulshiller-Aronov corrections and localization. So can you do something analogous? Can we ask this question in some better framework like quantum circuits or something simpler? That's my question to all y'all. But that's not what I'm talking about today. So I'm going to talk about two topics. Both of these are papers by my recently graduated student, Xinghai Zhang. He's staying on as a postdoc in my group for 1 year. And the first part is a story about classical hydrodynamics in a topological edge. And the second story, if I get to it, involves fractal-mediated superconductivity. So, I think a lot of us are interested in non-equilibrium quantum dynamics, quench dynamics, Floquet dynamics, things like this. And often we're interested in pretty special quantum systems. So quantum systems that are protected in some sense, because if they're not protected, then you drive them and they very rapidly thermalize, and maybe there's nothing interesting there. So things like integrable systems, or maybe effectively integrable systems like many body localized systems, low dimensional systems, 1D, for example, where things are strongly kinematically constrained, or in the last 15 years, topological systems, say. And then we can ask questions in such systems in special regimes, like say a pre-thermalization plateau regime, where you can have something like a collisionless steady state and coherent many-body quantum dynamics. And so the question with this first talk, which is going to end up being about shocks and bounces, which is actually not what we originally were intending to study here, the question we wanted to ask was, well, how do we deal with thermalization generically in one of these very special quantum many-body systems? So I want to think about thermalization in a not quite ideal quantum system, meaning it's not quite integrable, et cetera. And particularly in low energy effective theories, the types of interactions in such systems are frequently mediated by what you would formally classify as irrelevant operators in a field theory. Now, the problem with irrelevant operators, as any of you know who've ever taken, say, a relativistic quantum field theory class, is that we don't know what the hell to do with them, because they give rise to strongly ultraviolet divergent corrections. They're hard to deal with. And so, things like field theory methods seem to go out the door. And the standard way to try to do something is semi-classical hydrodynamics or kinetic theory. And so that's what we're going to do here. So the setup is a system that hopefully is familiar to many of you. So we're going to study dynamics in a 1D helical edge liquid. So these were originally proposed in the context of 2D Z2 topological insulators. So I've got a 2D Z2 topological insulator, say in a semi-infinite geometry. So I've got an edge. And then in the idealized quantum spin Hall case, I have right movers that are purely spin up and left movers that are purely spin down. And this is a sort of trivially integrable system because I can't backscatter without changing spin. So if the Z component of spin is conserved, then these guys just live their ideal lives. If you've worked at all on topological insulators, you're perhaps aware that 2D TIs are actually kind of crappy. The materials are not very cooperative. So if somebody was going to realize the dynamics I'm going to talk about in an experiment, you probably would want to do it in some type of multi-layer graphene these days. There's nice synthetic realizations of these types of edge states in various flavors of that system. Also, in principle, you could look at edge liquids of higher order TIs. So the setup is the following. So let's think about this ideal, trivial, non-interacting system. And what we're going to do is we're going to prepare a non-equilibrium situation. And what we had in mind is imagine you pattern like a micron by half a micron mesoscopic mesa in, say, a 2D topological insulator. So you have your circulating edge liquid around the perimeter of that mesa. And then we're going to apply something like a terahertz pulse. So an electric field whose wavelength is essentially infinite, so it's homogeneous. And we're going to apply it along a particular edge. And so what's going to happen, this is just two independent quantum Hall systems, is I'm going to take a bunch of spin up particles, which are left movers on this edge, and I'm going to Laughlin pump them across the system and accumulate them here. That's the red. I'm going to take a bunch of spin down left moving particles on this edge and Laughlin pump them through the system, and they appear here as a spin down excess. So what I'm going to get is an accumulation of spin here, but in two varieties, positive and negative charged lumps. And I'm going to get a depletion of spin on this side, but again, in two varieties of positive and negatively charged lumps. And now, if I just have this sort of trivial system, then what's going to happen is that all of these edge modes just propagate at the edge velocity, so they're going to separate and circulate around this mesa. And just to convince you that this is what happens in a lattice model, you can take the Kane-Meline model and do a quench with the electric field, and this is exactly what you find. So this is the short length along which the electric field is applied. This is the long length where we're going to watch our wave dynamics. And so you apply the field, you get a spin excess, a spin deficit, and then these things round the corners and become well-defined spin packets. Here at later times, you just have these propagating spin packets. And you can also look at charge, and it's basically the same, except now we have equal and opposite charge bumps circulating around the system. Okay? So that's what you would have in the absence of interactions. So what we wanted to do was ask this question, well, what happens to these dynamics if I consider some type of irrelevant interaction and I ask, how does it thermalize the system? And we sort of had in mind initially that, well, if I turn on some scattering, I'm just going to get diffusion and everything will go away. But actually, what seems to happen, at least in chiral hydrodynamics, is something more interesting. I get some highly dissipative shock fronts, and I can even use them to create current bounces. So here's the idea. So in a 2D topological insulator that is non-ideal, meaning I have some amount of Rashba spin orbit coupling in the system, then you still have spin polarized edge states, but as a function of, say, momentum along the strip, there's a slow rotation of the spin quantization axis. Okay? So, these guys are not purely, say, spin up, these are not purely spin down. And what this enables is if, in addition, I've got Coulomb interactions, and let's talk about, say, screened Coulomb interactions. I've got a gate somewhere nearby. Is the combination of Rashba spin orbit coupling and screened Coulomb gives rise to a pretty weird one particle umklapp scattering process. So the process is the following. I take two right-moving electrons, and what I do is I scatter them into a single left mover and a single right mover. And the kinematics are very strange in the sense that I take the momenta of these two initially right-moving guys, I sum their momenta and give it entirely to this new right mover, and then the left mover just goes to zero momentum. And now what's zero momentum? This is a well-defined notion on the edge of a topological insulator. It's the edge Dirac point, the gamma point of the edge, if you want. And I'm going to assume I'm doped there. Okay, and this is just following from momentum and energy conservation, this weird kinematics. And if you want, you can write down an effective interaction Hamiltonian, which involves, like, say, 3 right-moving operators and 1 left-moving operator. So because of this extra derivative, these interactions are formally irrelevant. So this is, well, so that's another type of irrelevant operator that you can include. We did not include that here. But we actually get shock dynamics just from just from collisions mediated by this interaction. So if I put some additional curvature into the edge, then yeah, that'll probably lead to additional dispersion. We did not include that. So, I mean, if you've studied 1D systems, you're probably immediately asking, well, what about Lunder liquid physics? And my answer is, well, we left it out. If you want to put it back in, which maybe would be a nice project, you could do it. And the way you should do it is you should bosonize the system and refermionize in terms of effectively non-interacting, but fractionally charged right and left movers. The only price you pay then is that this one particle umklapp interaction becomes non-local because of strings, but it's still irrelevant for any coupling. So that means, at least philosophically, I should still be able to write a kinetic equation for the new right and left movers and calculate the collisions based on now this funkier version of the interaction. But we did not do that. We did not include Lunder liquid interactions. So the question we just wanted to ask is, what is the effect of these collisions on these circulating charge packets? And well, we don't know how to ask that quantum mechanically, so we formulated it classically. And we just are going to do chiral hydrodynamics. So I'm just going to write continuity equations for the left and right densities and left and right momenta. Right? So this is the Newton's equation. On the right-hand side are the forces. So there's the electric force when I'm applying the electric field to generate the excesses and deficits. There's also a friction force that in general will act between the left and right movers. In terms of the continuity of the particle numbers, there's the axial anomaly. This is what enables me to do that pumping at the beginning. But then there is an imbalance term, which is mediated by these inelastic collisions. Actually, both the imbalance term and the friction are mediated by these inelastic collisions. But actually, once the field is turned off, I can forget about the axial anomaly and the electric force. And it's also a funny feature of this interaction, but also the usual sine-Gordon interaction, that actually the momenta are separately conserved. Okay, so right and left momenta are conserved, but particle number is not. Particle number, I could still turn right movers into left movers via this process. And so I still have to deal with this imbalance relaxation. So technically, what we do is we derive some self-energies in the Keldysh framework, convert it into collision integrals, and then we're going to assume local equilibrium in order to evaluate this thing and get a closed form expression for it. So what kind of physics could we expect here? Well, so I'm just rewriting these equations again. I can kind of compactify them if I switch to light cone coordinates, set the Fermi velocity equal to 1. And so again, just right movers and left movers that are being interconverted by this imbalance force, which depends on the right and left densities, and also in principle, the right and left temperatures. We're doing hydrodynamics, but the momenta are separately conserved. So let's imagine we've done this thing where we apply the electric field and we make these circulating charge packets. Let's look at what's happening to, say, a circulating right excess as it's propagating. So imagine I have, like, say, a Gaussian profile, this thing. Well, this continuity equation translates into a local relationship for the right and left temperatures in terms of the densities. Okay, so I'm working at finite temperature. So my initial temperature is some T naught. And I'm going to assume that this N naught, so I've set the Fermi velocity equal to 1. And so everything is measured in terms of inverse length units, like relativistic quantum field theory. So I'm assuming that this initial excess is much larger than T naught. That's where the dynamics is interesting. And so then what this sort of trivial continuity tells you is that the right moving temperature is going to deviate from T naught once this imbalance starts converting right movers into left movers, right? So I've got a right excess, I have a way to create left movers, I'm gonna start equilibrating. Okay, so that means this N sub R is gonna decrease and the temperature of the right movers is gonna go up. Interestingly, for the left movers, all I can do is decrease the temperature because I don't start out with any left movers, so I'm actually gonna cool the left movers. And okay, so this looks like a very simple problem. I just have to solve this equation subject to these constraints. This I is horribly nonlinear in terms of NR and NL. And as somebody who usually does quantum field theory for a living, I don't have that much experience with dealing with truly strong nonlinearity. So we're kind of surprised about what comes out of this. You could do something stupid like short time perturbation theory. And what you find there is the following. So immediately I start heating in the middle of this right moving blue packet, and I'm converting right movers to left movers. And then I'm firing out left movers with some amplitude, and the maximum that this amplitude can become is set by the temperature I'm starting at. But actually, when you solve this problem numerically, this isn't at all what happens. So you could just solve this problem by, say, considering a finite edge loop and solving the equations in terms of momentum modes, just doing Runge-Kutta. So this is what happens. So this is at some very short initial time. So I have this initial Gaussian packet of right movers. And indeed, so what I'm plotting here is the density, NR, that's in red, and blue is the temperature. And so indeed, initially I start heating in the middle of the packet, but very rapidly, actually, the temperature concentrates on the forward face of this propagating packet. What's happening is that I'm very rapidly actually equilibrating through the middle of this, quasi-equilibrating. And it will turn out, I'll show you in a minute, that this imbalance force very rapidly focuses itself only close to this forward moving face. And so what I'm doing is I'm converting right movers to left movers. And I can do that as long as I'm doing that at a certain rate. I can actually cancel the imbalance through most of this charge packet. But the price is I have to be supplying the left movers from somewhere. And the place they're coming from is this forward moving face. So if I plot NL and NR, here, this is very short time. So you just have this mainly Gaussian wave packet, but it's starting to steepen at this front. The left movers are being emitted. And again, the density at which they're being emitted is close to the temperature T0 here. Everything is normalized in terms of the height of the initial right moving packet. So if you wait longer, well, you get a shock front. So the face of this propagating right moving packet is melting continuously as it converts right movers into left movers. So here you can see this red packet. And again, I'm heating locally, only substantially at the front of this propagating packet. The amplitude of the left movers is stable. And if I plot the imbalance, it's 0 almost everywhere except right at the forward face of this propagating wave. Okay. So this very simple nonlinear wave equation self-focuses itself and creates this shock front as a way to minimize, as a way to quasi-equilibrate almost everywhere, but it has to be converting somewhere in order to accomplish that. Okay, and you could quantify this a bit. I don't know how interesting it is, but you can look at the decay rate of the total density, the total right moving density as we're converting it into left movers. And it goes like 1 over temperature for low temperatures. You can also quantify it in terms of the interaction. It goes like 1 over W squared. That's a Fermi's golden rule argument for small w, but then it asymptotes to some constant value. So the second part of the story is, well, how would you ever detect this? It would be very hard to actually experimentally detect these accumulating shock fronts. So we thought, well, what if we imagine patterning mesas of this two-dimensional system, and we induce these circulating packets, but now we've got interactions. What would those interactions do? Well, if you think about the non-interacting case, and imagine I create a whole bunch of these mesas, and again, I send in a terahertz pulse, and that creates these circulating packets. So every period, I get 2 circulating packets with equal and opposite charge that are going in opposite directions on the side of the mesa. And that gives me a coherent current in one direction. And every half period, I would get the current going up and then down as the packets go around the mesa. But it turns out that if we include the effect of the strong imbalance, then what I can do is actually get perfect bounces. Well, not perfect, but I can get near perfect bounces between these propagating right and left movers. So here you have an incoming right moving shock front, an excess. There's that hot imbalance. So here I'm plotting the imbalance on the right-hand side. Here I have an incoming left deficit. And instead of passing through each other, which is what they would do in the non-interacting case, they sort of squish into each other and then bounce back, so that now I have a left propagating excess and a right propagating deficit. And so if I plot the current as a function of time, in the non-interacting case, I would have this switching like this. But in the presence of these bounces, I would get double switching, because every time the packets are bouncing, the current would go up and down. So there'd be a frequency doubling. Here's what the dynamics actually look like. These two things smash into each other. Come and collide. And when this is happening, again, the imbalance is focusing only at the place of the collision. And you can look at this as a function of different interaction strengths. So if here the red is for interaction strengths from 0 to 5. Again, everything is in inverse length units. W actually has quantities of length because it's an irrelevant interaction. And everything is measured in terms of the right moving density excess. And so as I tune it from very weak interactions where we have the switching every other time behavior, there's some kind of critical regime where very rapidly the thing just thermalizes, but then for stronger interactions, I start to get this double switching. All right, so that's one story. That's a story about these shock dynamics. So how am I doing on time, actually? Okay, good. So I have enough time to tell a completely different story. So the second story, which has nothing to do with the first one, is about fractal-mediated superconductivity. So just first preface this. So probably some of you at least have looked at or worked on Anderson localization and or many body localization. So there's these different metrics you can use to try to decide if your system is localized or not. And one of the ones that was very popular in the heydays of MBL was level statistics. So what I'm plotting here is for a certain 1D non-interacting Hamiltonian. Technically, it's a power law random banded matrix model. This is a model that goes through a metal insulator transition even in 1D because it has long range hopping. And technically, you're tuning here the power law of the hopping. And so what you see is that I'm interpolating between Wigner-Dyson statistics, which I have in the ergodic phase, and I'm getting pretty close to Poissonian statistics as we go into the Anderson localized phase. But I guess the thing I want you to take away from this animation is it's not very easy to figure out where the system is localizing. Actually, here, let's do it one more time. It's about when you start to see the hole fill here. That's essentially the metal insulator transition. So it's when level repulsion, so about there is when level repulsion is turning off. But still, it's not such an easy signature. Another thing you can look at is the inverse participation ratio. So I diagonalize this Hamiltonian. I take each eigenstate, take its probability. Of course, if I sum the probability on all sites, I just get 1. But instead, let me sum the probability squared on all of the sites. If the wave function is strongly localized, then this object will be large, of order 1. If, on the other hand, the wave function is extended through the whole system, then this will be small. So here I'm plotting this for all of the eigenstates of this special Hamiltonian in 1D. One thing to notice is that most of the eigenstates are behaving the same way. That's a very special property of this model, that it has a so-called spectrum-wide metal insulator transition. And so somewhere here, actually it's about there. So this is the log of P2. That's the metal insulator transition, where all of the states are becoming Anderson localized. Again, it's a little bit hard to figure out just staring at this animation where the transition actually occurs. So actually, my favorite diagnostic is one that was not discussed much in the context of MBL, although maybe it should have been. And that is this Chalker scaling correlator. So what I want to do is I want to kind of take the inverse participation ratio and point split it in energy. Okay, so I'm going to take a wave function, say at the center of the spectrum, and take its probability, multiply it locally by the probability of some other wave function anywhere else in the spectrum, and sum that over all sites. And then I'm going to normalize it by the inverse participation ratio of the two wave functions. So that should be E2. It's a typo. Okay, and so I've done that for this funny model. And what you see is that initially, I have like a smooth curve. I start to develop a cusp. But then at the transition and beyond it, this becomes pointillized and strongly suppressed. And that's a key feature of the Anderson insulator that distinguishes it from the metal insulator transition, which is that at the metal insulator transition, the wave functions are kind of like cat states of Anderson localized peaks. But there's a key difference. In the Anderson insulator, localized peaks from different wave functions that are nearby in energy are completely distant from each other in space. At the metal insulator transition, they tend to nest right on top of each other. This is the only reason the scaling theory of localization works. The reason why you get a smooth behavior as a function of energy. So this was pointed out by Chalker, well, way back when. And here's just another illustration. Here are 4 2D localized states nearby in energy. They have essentially 0 overlap. So in an Anderson insulator, the Chalker correlator is a sum of discrete delta function peaks. But for states near a metal insulator transition, so here are 4 such states, what you see is that these peaks tend to nest like Russian dolls. And that is this feature of Chalker scaling. Okay, and technically, there's a prediction for a non-interacting metal insulator transition that this correlator should scale as the energy difference to some exponent. And this exponent depends on this fractal dimension D2, which is exactly the anomalous fractal dimension that determines the scaling of the inverse participation ratio at the metal insulator transition. Okay, so that's some non-interacting metal insulator transition physics. Why should you care? What the hell does it have to do with superconductivity? Well, here's the answer. So imagine we add Hubbard-U interactions, say attractive Hubbard-U interactions to this special one-dimensional model that has a metal insulator transition. Now, if you think about the interaction matrix elements in terms of exact single particle eigenstates of the non-interacting problem, here's the key point. This object scales like 1 in the metallic phase. At the critical point, it scales like the inverse participation ratio times the Chalker correlator. And in the Anderson insulator, it scales like L over the localization length multiplied by the Chalker correlator. Here, D is 1 because we're in 1 spatial dimension. So it seems like actually in an insulator, you're getting a very strong boost of the interaction matrix elements, but you have to keep in mind that most wave functions don't sit anywhere near each other in the Anderson insulator. So actually, because this is just a delta function, it has minimal effect. But at the metal insulator transition, you have this smooth scaling in energy. And so as a result, you can get a strong boost of local interactions at a metal insulator transition. So interactions can be strongly enhanced. Okay, so what about disorder in a superconductor? Well, sorry, how am I doing on time? 6 minutes, okay, we'll get there. So, most superconductors are actually in the dirty limit. So most garden variety low temperature superconductors are in a limit where, yes, 1 over tau elastic is much, much smaller than the Fermi energy. They're good metals. But delta, on the other hand, is actually much smaller than 1 over tau elastic. They're actually very dirty systems in terms of the superconductivity. But way back in 1960, Anderson said, well, think about pairing exact single particle eigenstates, and then you can convince yourself that TC should remain unchanged. And this is basically coming to this point that the matrix elements do not scale with disorder in the metallic phase. You can also do this diagrammatically by summing the Cooper ladder, and you get back the usual BCS prediction. Dressed by impurity lines, you get back the usual BCS prediction. But back in 1982, Fukuyama and Meikawa asked, well, what about the effects of Anderson localization? And they computed some interaction-dressed diagrams, technically involving the Coulomb interaction. And what they actually found was a strong suppression, well, not a strong suppression, they found a suppression of TC by computing these diagrams, and they said, well, this is somehow a signature of the system becoming Anderson localized. So how does that jive with the story I just claimed to you that short-range interactions can be generically enhanced? Well, it turns out that in the case of solid-state superconductors with Coulomb interactions, that's a special case. So with long-range Coulomb, generically you suppress the transition temperature. It's a quantum interference effect, but it's a suppressive effect. However, if the interactions are short-ranged or they're spin-mediated or something else, then generically you actually get an enhancement of the transition temperature. At least that was the prediction in a bunch of papers by Feigelman and company about a little over 10 years ago, that you could get a transition temperature that, say, scaled like the interaction to some exponent, and that exponent is determined, again, by our friend, the fractal dimension of the eigenstates. So we decided to investigate this numerically in two 1D models that have a special feature, which is the spectrum-wide quantum criticality. So one of them, I'm sure you all know and love, it's the Aubry-André model, particles hopping on a lattice with an incommensurate potential. It has extended localized and critical phases. Of course, you all know that the energy spectrum itself, if I choose some particular beta p, is fractal at the critical point, which is when this v is equal to 2t, or t is equal to 2v, anyway. However, what's less appreciated is that actually all of the wave functions associated to this fractal energy spectrum are multifractal and critical at the metal-insular transition. And so this is this feature that we call spectrum-wide quantum criticality, which is weird. It happens in this model and one other 1D model, which I'll mention, but it seemed to only occur in these funny 1D models. The reason we decided to actually investigate this here is that we very recently found evidence that, at least under pretty generic conditions, surface states of 2D topological superconductors, but also D-wave superconductors with quenched nematic randomness show this feature as well. It's much harder to do self-consistent BCS numerics with 2D wave functions, so we decided to do 1D. Okay, so we're going to just do self-consistent BCS numerics, and here are eigenstates for Aubry-André, extended, localized, multifractal. So we're going to take this, just do self-consistent BCS, the same thing that was done by Trivedi and company way back in 1998 for the 2D Hubbard model, incorporate the Hartree shift. We also compute the BCS superfluid stiffness. Long story short, here are the answers, the results. So this is a map of the incommensurate potential strength V versus the attractive Hubbard U. What's plotted here is delta. Okay, this is just self-consistent BCS theory. That's all it is, Hartree-Fock. So the white curve is the curve indicating the maximal enhancement of superconductivity. These colored curves are different ways of extracting the metal-insulator transition for different system sizes. And the key point is that until the interactions become of order 1, we actually have these curves essentially lying on top of each other. Or another way of saying that is that we can locate the metal-insulator transition by looking at, this is actually D2, this fractal dimension I talked about before. Well, it's D minus D2, it's related. And in the metallic phase, it's 1. In the localized phase, it's 0. And so there's a sharp transition at the position of the metal-insulator transition. The metal-insulator transition does shift as a function of interactions due to the Hartree shift, but it still appears to be spectrum-wide quantum critical. And at the metal-insulator transition for these different U's, we see this strong enhancement of superconductivity. So you should also, in a dirty superconductor, you should also look at the superfluid stiffness, because just because you have a local enhancement of the amplitude does not mean that you're going to get a higher TC. Now, of course, this is a 1D system. You're not actually going to get real superconductivity, but our real interest is in eventually repeating this in these 2D systems that show spectrum-wide quantum criticality. But nevertheless, in this 1D system, we wanted to cover all the bases. So we computed the superfluid stiffness. And the actual TC, if this were a higher dimensional superconductor, would be governed by the minimum of delta and the superfluid stiffness. And although the superfluid stiffness monotonically decreases as a function of the incommensurate potential, the point is that actually, until you get into the Anderson insulator, you're actually dominated by the amplitude. So the superfluid stiffness is quite large until you get deep into the Anderson insulator. It's also interesting to note that the statistics of delta, in the ergodic phase and at the metal-insulator transition are strongly multimodal, but delta itself is not multifractal. There have been a few claims of multifractal superconductivity in some transition metal dichalk cogenide superconductors, but I don't think delta itself should be multifractal. It's the wave functions. Now, and I'm probably very short on time. Okay, so let me finish. So one problem with this model is that the energy spectrum itself is fractal, which means that the bands are becoming very, very flat near the transition. So there's probably a boost of the superconductivity just coming from the density of states. So here is delta, and here's the bandwidth for u equals 0.5 and u equals 1. And the peak is close to where the density of states is becoming minimal, although as we go into the Anderson insulator, the peak is rapidly dropping. But we decided to look at another model, which is the power law random banded matrix model. That's the one I showed you Chalker scaling for before. And the point is that this model does not have any interesting features in the density of states. So long story short, we do the same thing. Now there's a parameter alpha, which is the power law controlling the hopping. And again, we find a ridge of most enhanced delta. The colored lines are the metal insulator transition. And here's delta versus the fractal dimension that indicates the metal insulator transition. Again, we seem to get a largest enhancement, essentially commensurate with the metal insulator transition. Okay, so indeed, multifractality can strongly boost superconductivity. I don't have time for this. Long story short, there's evidence in D-wave superconductors of something strongly inhomogeneous going on. Maybe it's spectrum-wide quantum criticality. And okay, so I told you a story about shock and bounce dynamics and fractal superconductors. And I said, hey, somebody should really look at quantum hydrodynamic modes using tools that I don't know about. And that's it.
Thanks, Matt, for the firing shot. Okay, so it's time for questions.
So in the Aubrey-Andre case, I guess one surprise to me is that you found a big super density. The Feigelman theory, of course, was a theory of like very sparse puddles, right? The tiny superfluid density. So do you also see a big superfluid density in the PRBM case?
So we didn't. That's a good question. We didn't calculate it
some kind of Aubrey-Andre pathology, because as you say, there are lots of Aubrey-Andre pathologies.
So I don't think it's a pathology here in the sense that, so Feigelman talk about the picture you would have for superconductivity near the metal insulator transition, as opposed to the superconductivity that can actually go beyond into the Anderson insulator as long as the coherence length is much shorter than the localization length. And so their prediction for the statistics of delta is associated with what they would call a multifractal metal, meaning multifractal on short scales, but then actually just some uniform average background outside of that. And that's actually consistent with what we see. We do not see multifractality in delta itself in Aubrey-Andre. We did not compute stiffness in power law random banded just because you've got to introduce gauge strings on all scales. So it's slightly tedious.
But just to understand, we should be talking about the multifractal insulator, right? Not the multifractal metal, because that's the regime in which there's sort of this non-trivial remnant superconductivity.
Yeah, the multifractal insulator, that's right. But they also, so they predict an enhancement at the metal insulator transition, but also going into the insulator as long as the localization.
And in the insulator was where I understood the picture really was a bunch
of puddles. Yes. Yeah. So we're far away from that, right? So we're asking again, I didn't have time for it, but we have this picture of quantum critical states at all energies that seems to occur in certain models of 2D topological surface states, and may also be relevant to D-wave superconductors with random pneumaticity. And so one of the questions is, does it have some role? Yeah.
Any more questions? Maybe let me ask one more general question. So in the second part of your talk,
yes,
you argued that you want to actually understand the 2D system, but
yes,
computational difficulties,
yeah,
the system. So can you comment on, actually what kind of